Hello friends, hope you are having a fantastic day today. So once again, we are going to do an awesome LeetCode problem that is extremely popular at all sorts of IT companies. So without any delay, let's get started. So the LeetCode problem we are going to solve today is called largest rectangle in a histogram. This is a LeetCode hard problem and also an extremely well-liked problem. Now the statement is quite simple and straightforward. We are given an array of integer called heights that represent the histogram's bar height, and we are also told that the width of every single bar is 1. Now we need to return the area of the largest rectangle that we can make inside this given histogram. So this is all we need to return. And now let's try to understand this with an example. So for this, we can make a rectangle that looks like this. Now the area of this rectangle is going to be 2 because the width of this portion is 1 and the height of this portion is 2. So 2 times 1 is going to be 2. So same way, there are multiple different options we can have in order to generate the area, but we need to find the maximum area. And in this case, the answer would be retrieved using these values, where if we make a rectangle like this using these two bars, so now in this case the area is actually going to be 10. Why? Because the height of this portion is 5 and for this one the width is 2, so 2 times 5 is going to be 10. So this is what we need to find and this is what we need to return. So brute force approach is actually quite straightforward and very simple. Now one thing we can do is that we can take this one single rectangle starting at position 0, and then we can see that what are every single possible areas we can make. So one area would be like this, second area would be like this, the third area would be something like this, fourth area would be something like this, and so on and so forth. And eventually we do every single possible combination based on every single position of the given rectangle bar height, and then eventually we would find a solution like this that contains the most optimal approach, and this solution would work fine. We would be able to eventually find the answer, but this is going to work in big O of n square time, because at every single time we are doing a lot of extra and overhead work. So what is the most common thing we can imagine? Well, number one observation we can make is, because we can see that the height for this 0th index is 2 at the moment, but the moment we want to consider this first index as in combination with this 2, then the maximum height we can imagine is only going to be able to 1, which means we are only at the higher height until we encounter a height that is lower than our current height. And whenever that happens, we will have to start considering the lower height, and we need to understand a couple of things. If we want to calculate the area, we need two items. First item is the height. So we already know that which height are we going to consider based on the lower height compared to all the other possible heights. That is number one observation. Second observation is we need to consider the width. So width we can simply calculate based on the current index position where we have, or we can also keep track of that where did that height started existing. That in terms of finding the right side boundary of any particular rectangle, we can only find it until we find a lower height that reaches. So there are actually 3 examples we can see very easily. First example is at this position number 2, or this initial first position where the current height is 2 and the current height is located at position number 0. But the moment we try to consider the next element, we will have to get rid of this height too, because now it is no longer in the existence, which means the maximum area we are being able to generate using this bar 2 is only going to be 2. Okay. Now next thing, another example is we just saw with the value number 5, that with value number 5 we can only say that we can use rectangle 5 or bar 5 until we reach to this index position number 4, and then so which means maximum area that this bar 5 can make is going to be of width 2 and height 5, so total is going to be 10. Same way for this 6 comes into the existence at index number 3, but since the height at index number 4 is actually lesser than the index number 3, which means this 6 only remains in existence just for one single bar. So the maximum area we can make over here is only going to be of size 6. And this is the whole logic. This is the whole meat of the solution. Now, after understanding this, we can actually make a suboptimal solution using the same very simple approach, and then we will try to improve upon that solution. So the suboptimal solution that I'm proposing is that at every single position we identify that what its right side boundary is and what its left side boundary is. So what is the maximum height and width we can make, and based on that we can do all sorts of calculations and then find the solutions very quickly. So let's try to see this solution in action. The idea is at this position, the maximum left side height we can make is 2. The maximum right side height we can make is also the maximum width we are able to achieve is 1, which means the maximum area we can generate is only going to be 2. For this position number 1, the maximum width we are able to achieve is going to be 6, because this 1 remains in existence throughout this whole process, and the maximum height we can achieve is only going to be 1. So over here maximum area we can make is only going to be 6. Now at this 5, the maximum left side we can go is only up to 2, because it starts at position 2. The maximum in terms of right we can go is only up until position 4 or before position 4, so up to 2 and 3, so width is going to be 2. So over here we can make the area 10. For this height 6, we can only make the maximum height as 6. Same way at this position number 2, the maximum we can make is actually going to be this much, where currently the width is going to be 4 and the height is going to be 2. So maximum area we are able to generate is 8. And same way at this 3, the maximum we are able to generate is simply going to be just this one, because one before that is actually in the lesser height. So we can maximum area we can make using only or the entire height of this area is going to be 3, and in the end we can simply return 10 as the answer. So what we did is, for every single element we try to see that what is the left limit, what is the right limit, and what is the total area we are able to generate, and then we can very easily store the answer. Now this solution would just be good if you provide this solution in an interview. It might even work, but the thing is there exists a better solution, where if we just use stack to keep track that what is the current index position and until what previous index positions we are maintaining that height, then we can very easily solve this problem. Why we need to use the stack? Because think about it, for every single position we are only going to have that position in existence until we find another bar with a lower height, which means the moment we find another bar with a lower height, we can actually go back to the elements that are already present inside the stack with the higher height and calculate the area. That's it. That is the whole logic. So now let's try to see the solution I'm proposing in action. So now let's just quickly initiate our stack. Now inside the stack, we know that this is going to operate in terms of last in first out principle. And the other thing is, we can actually keep track of the bar heights, but then we would also have to find that what was the initial position of this particular value. So rather than, a better approach is that we actually store the index values, and using the index values we can quickly look up that what has been the bar height at that position in big O of one time, because we already know the index position, and then we would be able to also calculate the width depending on the current index position and the existing index position inside the stack. So let's try to see the solution in action. So initially stack is empty, okay, and we are also going to have a variable where we are going to store the area. So let's just mark this one as max area that we have been able to calculate so far. Okay, so initially stack is empty. Now we are at this index position number 0, so we add index position 0 inside our stack. Okay, and currently we know that this height is 2. Now next thing is, we iterate over to the next element and we identify that currently we are at index position 1. So the height at index position is actually less than the height we currently have on the element that is already present inside the stack, which means this position of this element 2 is no longer relevant, because we found out a value that is lesser inside in its existence, which means this only exists until this portion. So we will try to we will pop this element out and we will calculate the possible area that this element has been able to generate. So currently for this first position, this has been the area it is able to generate. That area is going to be 2, that is the height, and multiplied by width, that is 1. So the maximum area we have so far is 2. Okay, now once again we are going to add value number 1 inside our stack, saying that currently 1, so the height of this 1 is also 1, and currently we will only pop 1 out when we either reach to the end of the array or end of the heights, or we find some place where the height is actually 0 and then we have some more elements. Okay, so this is always going to be relevant in this example. Now we are at index position number 2. So notice what happened at index position number 2. The height suddenly increased compared to what the height we already have, which means this 1 is still valid. So because it is still valid, we are going to keep it inside the stack, not popping it out, and we will add one more element 5 or this index position 2 on top of the stack, because now this is also relevant so far. So we are going to put 2 inside the stack, so its subsequent value is bar height 5. Then we identify height 6, which means this 5 is still relevant. So because 5 is relevant, we are once again going to add value number 6 on top of the stack, or sorry, not value number 6, but the index position of 6, which is value number 3. So we put value number 3 inside on top of the stack, and the height is 6. Now we suddenly encounter the value at index position number 4, that is height 2. So any single value that has greater than 2 height has to be popped out of the stack, because now that is no longer relevant, which means first of all this 6 is now no longer going to be relevant because the height is 6 and currently this index position is 3. And notice that the index position for this bar height 2 is 4, which means depending on the index position difference, we can actually calculate the width for which this 6 was relevant. So 6 was currently relevant for width 1. So currently let's pop 6 out. If we pop 6 out, currently this 3 is no longer present. We know that this was relevant for 1 width, which means width was 1 and the height was 6. So now the maximum rectangle we have been able to find is of size 6, which is greater than the previous maximum we had. So we are going to update that. Okay. Now are we done? No, because this is 2 and this value is 5, which means we would still have to pop one value out. If we pop one value out in this case, now notice that the height at this position is 2 and the height at this position is 4. So because this is a greater position compared to over here, so what is the width we found? The width is actually 2, and what is the height we have is 5. So this is the height, and also let's get rid of this 2 from our existing stack. Okay, and now this area is going to become 10. So let's just add an area 10. Now once again we have this element 1 and currently this element is 2. So 2 is greater than 1. So because 2 is greater than 1, we are not going to pop 1 out because this 1 is still relevant. So we are just going to simply add 2 on top of 1. So let's just quickly add this index position number 4 with the height 2. Okay, and now currently next one we found the increase inside the height, which means this 2 is still relevant. Because this 2 is relevant, we are simply going to add an element 5 on top. So we are going to add element 5 on top. Now adding index position number 5, now we reach to the end of the array, which means the moment we reach to the end of the array, we will have to start popping every single value out compared to its current position. So currently we pop value number 5 out, which means what is the height over here? The height is 3. What would be the width? Width would only be 1 because it is only relevant for this one portion, because currently we are at the end of our loop. So the area we have been able to calculate by popping this value number 3 out is going to be 3. Now currently 3 is less than value 10, which is the maximum area we have. So we are not going to update the maximum area. Okay, now we are going to next pop out element number 4. So if we pop element number 4 out, it has been relevant for this much portion of the time, which means currently we have 2 multiplied by 2. So the area is going to be 4. 4 is also less than 10, which means this area is also not relevant. And last one, we will have to pop element number 1 out that has the size 1 or the height 1. So for this, height is going to be 1, and this has been relevant since position 1 until the very last position. So this has been relevant for the width 5. Oh, sorry, for the width 6. Since the very first position it has been relevant. So now because this has been relevant since position 6, so the maximum area we have been able to generate is also going to be 6, but still it is not greater than the maximum area. So after the end of this loop, we can simply return the max area to be 10. And that's it. That's the whole answer. Now if we see time and space complexity, in this case the time complexity is going to be big O of n, and the space complexity is also going to be big O of n. So the coding solution is actually quite straightforward. First, we have a variable called max area where we are going to be storing the maximum area we have been able to identify so far. Then we have our stack that we initialize, and we also have a variable n to store the length of the given array. Then we have our for loop to iterate over the given array. Now first we check for a condition that if the given I is equal to n, which means we have already crossed every single element, then we can mark the current height as 0, because this is to take care of the last element. If that is not the case, we simply take the value of the given subsequent height from the heights array. Okay. Now we have our while loop where we check that while the given stack is not empty and the current height that we have been able to identify for any given ith element is less than the current height that is already present inside the very first element of the stack, then we will have to calculate the area for that, where we simply calculate the height by popping the element out of the stack, and then we calculate the width by subtracting the value of the current I minus the current element that was present inside the stack minus 1. And then we calculate the max area where we compare two elements based on the given max area that we have been able to identify so far, and the given current height and width multiplication, or the current area that we have been able to identify. Whichever is greater, we are going to keep it that. And in the end, after we run out of this while loop, we are still going to push the current element inside our stack. And by the time we are done with all the elements, we should have our maximum area being populated with the correct value, and then we can simply return that. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And once again, our solution runs beautifully, extremely fast in terms of time and space complexity. So once again, the solution is present in the GitHub repository. The link is in the description, so you can check it out from there. Thank you.